Okay, we made it. The final roundtable of the day. I'm just gonna call back to the beginning of the day here, something I mentioned at the start that was the challenges and unknowns that we're in right now, and one of those included tech and AI. And yes, that is a challenge, but it also could be part of the solution. And when those two come together, if I can paraphrase Jesse with Malin from earlier, I like to put numbers to everything. It's really how you find a lot of solutions, and I think with this panel, a lot of them do like to do that as well. So, I will read the official title of the roundtable, which is Applied Metrics, Data-Informed Design Drivers for Environmental Impacts. I'll simplify that and just say that we have metrics that drive impacts. We've collected a range of experts from the industry, and I'll introduce them and bring them to the stage now. They'll each have about 5 minutes to give a spiel, and then we'll have a nice discussion afterwards. So we have Teresa Morosios from the University of Washington, Irene Martin from Arup, Kristen Dotson from Amazon, and Jack Rusk from C-Scale. If you all want to make your way to the stage, and then we'll set up the presentations and run.
Hi, everyone. My name is Teresa Morosios. I am a research engineer at the University of Washington Integrated Design Lab. I have a background in engineering, and I also have a license in architecture. So I practice as an architect, but missed academia, so came back. My colleagues at the Integrated Design Lab are Christopher Meek, who many of you might be know, Heather Burpee as a co-director of the lab. My colleague Deborah Sigler is here, as well as we always have amazing graduate students as well that work in the lab from the Department of Architecture. So I am going to be talking and sharing some research regarding building for performance metrics that we have been conducting over the past several years at the lab. Let's see if I can. Cool. So I am going to be focusing on work related to embodied and operational carbon, and I'm going to highlight two publications that have come out of our research group. One is a paper that was published in Energy and Buildings, and another is a report that was published with Cohn Pedersen Fox Architects and the Urban Land Institute, which is open access and available to download online. So before I get into these research projects, I want to just start with the research questions that guide our work. And these include, what are the trade-offs between embodied and operational carbon of building facade design? How do various climate types impact these trade-offs between embodied and operational? How does the carbon intensity of the electricity grid impact trade-offs? And how do trade-offs differ between different building typologies? So a lot of this work that we do is focused on facades. So first I want to start off with, why are we so interested in facades? I'm interested in facades as an architect because it's an aspect of design that has a huge impact on thermal comfort, the user experience. It plays a big role in reducing energy use, reducing peak loads, improving the occupant experience. So it's an aspect of design that is within the realm of the designer. And as you can see here in these charts, it contributes significantly to embodied carbon and also to end uses of operational carbon that are significant, like heating, cooling, and lighting. And you can argue the other aspects as well. So it is a main contributor to these, to embodied and operational carbon. In our work, we quantify embodied and operational carbon by measuring CO2 equivalent, which many of you are probably familiar with. It's a measure of estimating emissions of greenhouse gases that contribute to global warming. So it's a measure of global warming potential. And through our work, we do this for the embodied carbon of materials. And we typically limit our scope to looking at cradle to gate, so that includes the emissions associated with raw material extraction, transportation to a factory, and manufacturing. And for the operational carbon piece, our workflow is creating parametric energy models, assessing different designs of facades parametrically, calculating annual energy use, converting that to carbon emissions through emission factors of electricity and fuels such as natural gas. And then we look at these two metrics together to get a total sense of the total carbon impact of different design decisions. So to give you kind of a view of how we think about this and how we've studied this, and to put some of the findings of our research that I'm going to show in context, if we plot cumulative emissions over time, we can see that we have embodied emissions up front. That's the chart on the left, the darker line, and then we see how cumulatively the operational carbon emissions stack up and accumulate over the lifespan of a project. And this is showing a study period of 30 years. So if we assess various designs looking at embodied and operational carbon together, we often see that trade-offs between savings in operational carbon and investments in embodied start to emerge. So in this hypothetical example, there are different envelope designs that could be generated by using different insulation amounts in the wall. So you start from the first design not having any insulation, perhaps, and then increasing insulation so that you are reducing operational emissions, which actually isn't showing up very well here, but you're reducing operational emissions and then you're increasing embodied carbon emissions. And what we've seen a lot in our research is as you increase embodied emissions and you invest in insulation, let's say, there's an inflection point where there's a point of diminishing returns on operational emissions where the more material you add to that facade, you don't get as much of a return, and you actually, in terms of total carbon emissions, see an increase. So there's kind of this inflection point where if you look at embodied and operational together, you start to see a carbon sweet spot. So as I discussed, we typically assess this parametrically. So we look at different massing options, window to wall ratios, and different facade parameters, such as facade assemblies. We also take a look at this embodied and operational analysis in different climate zones and across different electricity regions, looking at regional emission factors. So I'm now going to dig into two of the publications that I mentioned at the beginning of my discussion, just to give you an overview of the types of findings that come out of our research. So in this first paper, which was a study of the trade-offs between embodied and operational carbon in building envelope design, looking at the impact of local climates and energy grids, we studied multiple simulation variables, looking at different program types, different locations, and different facade variables. And this resulted in about 26,000 simulation cases. And basically, this is kind of the sweet spot that I was talking about earlier, where you could see that looking at different envelope insulation values, 1 through 12, as you increase investment in that insulation in terms of embodied carbon, which is the green, you see a point of diminishing returns for the operational. And in this case in Seattle, the kind of sweet spot correlates with the code minimum. So going beyond the code doesn't really make sense in terms of total carbon. I also wanted to quickly share some findings from this report we conducted with the Urban Land Institute, where we similarly looked at case study buildings. This is one Vanderbilt in New York City, altered various aspects of the facade, and we generated charts that look at embodied and operational together. One interesting finding from this study is that mullion spacing made the greatest difference on total carbon emissions from all of the facade variables that we studied. And as you increase the module spacing, the mullion spacing of the curtain wall, the total emissions decrease because on the operational side, because of lower infiltration and thermal bridging, and on the embodied side, because you have way less material. So this was an interesting finding that we wanted to highlight, that this was the most impactful variable. And in Singapore, we looked at a case study building of what the impact of exterior shading was. And interestingly, we found this in a lot of different climates, that when you invest in exterior shading, it doesn't typically pay off in terms of total carbon emissions, because the operational carbon savings typically are not high enough to offset the embodied investment. But another metric that is really impactful is peak cooling, and that can be significant. So even though I've been talking about looking at operational embodied emissions, I argue that looking at peaks is also very important, because this directly correlates to the size of equipment, the efficiency of equipment, the types of equipment that you can use. It has impact on thermal comfort, and most importantly, I think it impacts the reliability of the grid and the ability to use, not rely on heavy fossil fuels during peak loads for the entire electricity system. So looking at peaks is another important metric for reducing carbon emissions. So I am going to leave it at that. Thank you.
Great. Hey, everyone. Really happy to be here. I'll keep it at a slightly higher level and a faster clip so we can get to the round table. I lead this small but mighty organization, C-Scale. We do data services and tools to help measure whole life carbon emissions from buildings, operational embodied, sort of as Teresa laid out. Our internal tagline is we try to get designers the right data at the right time to make the right decision. This sounds easy and convenient. It's actually very difficult to get all these things to align. Working backwards through this phrase to sort of dig at some of the complexity here, we're really interested, I think, as an industry, should be really interested in decisions, not just reporting and compliance, really the risk of a lot of carbon accounting and measurement as we get stuck in a world where we're worried about bean counting and backwards looking assessments. The goal of all of this is to make better design decisions, right? When we think about the right data at the right time, this is where actually a lot of complexity emerges. I think you can do a lot of cool analysis. You know, the one Vanderbilt example I think is interesting. That building's built and we can look at some of the variables, but really when any of us are in the thick of a design process, we're always balancing, we'll say, projective ideas about what we want the building to be with the reality that the building doesn't exist yet, right? We're in the middle of this process where only some data is available. This is one way we'll illustrate that sort of graphically. Imagine this is the design process moving right from left to right, and really the data is slowly, maybe we can say, building up over the course of it. The risk that we all face in using sustainability data to make decisions is we're going to wait until all the project data is available to be able to figure out what's big and what's small. Is it embodied carbon? Is it operational carbon? Is it the facade? Is it the structure? The risk being at that point, all those decisions are pretty well baked. We need better tools to make better decisions earlier in this process where we know relatively less, right? So an approach we take, and I think others in the industry are starting to take, is using predictive data. For us, we do a lot of machine learning. Other people have different approaches, really statistical approaches, the same way that folks who are working in the cost space use comps to fill in data gaps early so that all the decisions can be made in contrast. You know, people ask, what's the most important thing I can do to reduce carbon emissions from my building? The answer is always, it depends, right? Sometimes it's the facade, sometimes it's the structure, sometimes it's the refrigerants in the cooling systems. Often it's the interiors, actually, a scope that doesn't get enough attention in these conversations. The risk is that if we're stuck using heuristics and rules of thumb, not making data-driven decisions, we'll index on the things we know, which may not be the most important variables in the project. So early phase analysis that allows you to sort of fill in some of these gaps helps maintain context throughout this. What this means is that we are able to build iterative design processes. We're first setting a whole building strategy, really establishing which scopes we're going to look most closely at. Often it's structure. Maybe that's the concrete spec. Maybe it's an opportunity to do timber. Often, actually, when we look at many of the, we'll say, like West Coast buildings that are very leggy, you have really facade-driven emissions profiles, and that gives you the opportunity to focus there. And you look at retrofits, it's often the interior scope, but you work from a whole building strategy down to something like configuring assemblies, all the way down to material selection and detailed design. We've all seen this happen the wrong way, right? Where the building is being designed and you know the massing and you know the carpet you want to use. That's, that can be useful. But every project is necessarily resource constrained, and the risk of having the wrong resolution of data too early in the process means you might not be targeting what matters most, because really with all of sort of like sustainability focused design, we're trying to do more with less, and to do that well, we need to be very targeted. And I think the perspective I want to bring here, that data is what allows us to target what matters most throughout the design process. So I'll leave it there, and then we can get into the round robin.
So interesting, oops, sorry, wrong button. Okay, there we go. Interesting fact, I started in this industry 21 years ago, partially because of C-Scale's other co-founder, Brad Jacobson. He gave a guest lecture at Stanford when I was already a grad student, when I was taking Gilmaster's class on energy efficient buildings. So I have a background in environmental engineering, but then I did mechanical engineering for a couple of years, but really wanted to focus on passive design. So that's how I ended up being a facade engineer. So kind of bridging the scales of global down to building level, down to architectural detail level. So that's the one that I pressed earlier, and then this one, right? Okay, so I spoke to a couple of you earlier, and some of you are not familiar with Arup, but even if you don't know Arup, I'm sure you've come across some of our projects. We are a global engineering and consulting firm founded in 1946. We have over 18,000 employees. My first exposure to Arup was when I was 11. I have roots in Hong Kong, so when I visited Hong Kong for the first time, the Bank of China, HSBC headquarters really stood out to me. So I didn't even realize at the time that I would end up working for the same engineering firm that designed these buildings that I'm so personally drawn to. Here in Seattle, you will recognize some of the most iconic projects that we've helped and contributed to, although there are many more that are confidential, so I can't share all of them. Across the bottom row of these images are 3 of my projects, and I want to give you kind of a taste of the range of environmental metrics depending on the building typology. So we have the Museum of Anthropology in Vancouver on the bottom left-hand corner. For a museum project, the environmental metrics that are really crucial are protection, preservation of artifacts, but also the user experience. So, selecting glass that has a high color rendering index so that you view the artifacts in the way that they're intended to be viewed. Obviously, ensuring no water leakage that would damage the artifacts, that a lot of which are wood-based. The project in the middle is Google's Bayview campus in Mountain View, California. This is an open plan office space with a very deep floor plate. And the design team took a very integrated approach in terms of environmental metrics, from designing bird-safe glazing with a particular threat factor that we needed to meet for the glazing, to the integrated roof canopy design, which basically served 3 different functions. One was that because of the very deep floor plate, we had to have these clear story windows to bring the natural daylight deep into the space. Secondly, you can see that they're doubly curved panels, so our hydrology team actually had to optimize the drainage points to collect the stormwater and then, send it back to the on-site water treatment plant. And then the roof shingles are actually photovoltaic panels that generate electricity. And then in the bottom right-hand corner is a hospital building. So, a third building typology where, as many have mentioned previously, it's not about the energy consumption because hospitals are ventilation driven. So the facade actually has less of a role to play when it comes to energy consumption overall, but it has still a very large role to play when it comes to reducing peak heating and cooling loads. So we worked very closely with our Arup mechanical team. Anne-Marie is here today. Some of you may have seen her. She's leading this project. So it was reducing peak loads, but also mitigating condensation risk, which is something that we're seeing a lot of push and pull because energy codes are saying insulate your buildings, but with added insulation, especially towards the interior, you're also drawing that dew point line further inboard. So, detailing, layering that facade in an appropriate manner is really critical. Teresa already gave a really great overview of using whole life carbon as a tool. I wanted to use the concept of carbon payback periods, especially on existing buildings where a client might be trying to decide, do I just keep my building as is, or do I invest in embodied carbon, which is kind of considered a capital expenditure in order to gain back those operational savings. And by using a payback, kind of a carbon payback approach, you start off with that initial carbon spend at time equals 0, and then the operational savings over time. You can tell that with an option that has a higher initial embodied carbon could be like more insulation or better windows, but it gains you that operational efficiency much faster than the lower intervention option. But of course, we can't just consider carbon. If I give you the example of, we're in a region, the Pacific Northwest has a very clean grid. So I have heard architects ask the rhetorical question, okay, well, if I don't need to worry about operational energy and I only care about embodied energy or carbon, does that mean I can get away with something like an all glass box? And those of you who have sat in on my AIA talk will know the answer, or at least my opinion of the answer, which is no, because an energy efficient high performance facade design is still better in other metrics. It could be something as crucial as safety. Do we want single pane annealed glass, or do we want to laminate it for containment? That has a higher embodied carbon, but that's not tracked in the same metric. So, this is just a simple matrix with a lot of data going into the analysis, but this is how we present different performance metrics to our clients so that they can, really make the decisions based on their priorities.
All right. I failed yet again. I did not remind everybody. Slido, put your questions up. Luckily, we have time now to add them to the Slido because I'm going to ask a few. And you all answered a bunch of them already. But we will start with one for all of you. What matters most? And how do you measure that? Have at it.
I love that the owner perspective is everything, everywhere, all at once. You used to be at Miller Hole, projects have budgets. There's this thing called the billable hour, And I think so much of the work, where we see data providing a lot of value to the design process, is it allows designers to focus in on just a few things, but the few things that matter most. If, sometimes there's these trade-offs that obviously exist, decisions don't live in choices don't live in isolation. But rarely is there time to dig into every spec section, get it exactly right. That'll happen over time. Everybody should be working on improving their specs. But once you understand what the biggest sort of, we'll say, contributors are to a building's emissions, again, sometimes they're where you expect them to be in the concrete, sometimes they're where you don't expect them to be in the cooling system's refrigerant load. Once you're able to dig into that, you can say, okay, we're going to solve this problem and this problem and this problem. Hey, we've done 3 things to reduce 50% of the building's footprint. That's where everybody needs to get started. There's the long tail of small actions we need to really take seriously. Better details, and everything that designers do. Some of this is communicated, some of it is just what becomes good design. But really, I see the use of data in the design process as the thing that allows all of us to focus eyes on the prize, there's just not time in the day to solve 100 problems. Solve 3 really well and use data to figure out what those are.
To me, I think the most important thing is to kind of go beyond the discipline-specific systems and really kind of reach across the aisle, not just to other disciplines like how does my facade design impact your mechanical system design, but also collaborate with contractors who can give us that data and close the feedback loop.
In my view, I think my guiding light is a cleaner grid. So one thing that I was shocked about when getting into this research is the electricity emission factors for most regions in the US are dirtier than natural gas. So for a kilo BTU that for heating that's required by a building, it almost, in terms of carbon emissions right now, would be cleaner for that to be delivered by natural gas in most places in the US. So what that indicates to me is that we have a lot to do to reduce loads, to shift all of our energy consumption towards the cleaner sources, and like I said, reduce peaks so that our large loads don't have to be compensated by really dirty coal. So I think for me, reducing peaks and total operational carbon is definitely important.
Excellent. I'm seeing the first question here. We're going to switch it back to regionally. Teresa, considering the sweet spot for operational embodied carbon in Seattle is already code minimum, is there a good reason to go beyond the code minimum for an envelope?
In that limited study that we did, at least in Seattle for office and residential typologies, the answer would, if you're only looking at operational carbon and embodied carbon emissions, the answer would be no. The code minimum is already doing a lot. And you're seeing that inflection point or point of diminishing returns of in investing in operational if you go beyond code minimum. This varies a lot per technology or per typology of building, also by orientation. So there is a little bit of nuance I think that designers have to grapple with, but as a general rule of thumb, our energy codes are already performing fairly well if we're only looking at annualized operational and embodied carbon emissions. Things like peaks, again, might be worth going above and beyond code.
Tim, can I parlay that to a question for Irene? Because you mentioned I would love to take this question and ask you about the envelope to MEP equipment, and if there's a relationship there to expand the problem. Is there a reason if you can downsize mechanical equipment to go beyond the code minimum?
Yeah, actually, we have a very similar graph to what Mark Brun from PAE had shown previously, which was, if your peak cooling load is a certain level, you can get away with passive systems, or you can get away with radiant systems, and kind of moves up until you end up with VAVs, right? So yes, especially, so I'm based in Los Angeles, so a lot of our projects where the building envelope does play a big role in peak heating and cooling loads, peak cooling loads, not really heating loads. We look at a cutoff point for peak solar radiation. Solar heat gain is the big driver for peak cooling loads. And then we tend to start by using that as a proxy for what the peak cooling load is. Sometimes we use dynamic thermal modeling and incorporate everything like the conductive envelope gains, occupant loads, equipment loads, for a more holistic picture on what that peak cooling load is. But yeah, absolutely, we can quantify that and tie that back into what mechanical systems can be used.
We're going to tackle some of these questions on the screen here. I'm going to skip the first one because that's really where I went to end. So all of you start thinking about what's next. But before we get there, Jack, how do you evaluate your data-driven models? Are the evaluation results available?
Yeah, I think this is a great question. There's two dimensions to this. There's all the sort of classical approaches, statistical approaches we can take to say, how good are our models against the data we have already collected, right? And I can talk you through that stuff. It's relatively less interesting, I think. The more interesting part of this question is the way that every, we'll say building that somebody is working on will ever be that building. Like buildings are not, it's not like a Subaru. They don't just roll off a production line. They're adapted to the site. The question, how does this predicted data describe your exact building? Never exactly, right? But that, I think, is sometimes the wrong question. The earliest uses of these models that we built when I was at EHDD was to go after and win the AIA headquarters project in Washington, D.C. We made very early commitments to carbon targets. It was not because we had perfect knowledge, but we knew by patterns in the data that it was achievable. And we used the design process, which is never linear, right, but bounces back and forth, with those targets as a North Star. And it's by having that target that we were able to make it real. The risk is that you don't have a target, you don't start with data, you're bouncing around and you end up off track. There's no way that anybody with just you look at a massing, nobody's gonna know exactly how many screws go into that facade, right? But by iteratively working through the design process against a North Star goal, determine the data early on, that's really what makes these goals achievable. The risk, again, without data is that you go off course easily. So the kind of way that I think this question is more meaningful is can anybody exactly predict what my next building will look like? The answer is no, but early phase estimates still help you focus on the design decisions that matter most.
Excellent. I know we're coming up to time here. Do we have time for maybe two more?
We can answer all. You can go for it.
We keep going?
Yeah, for at least 5 more minutes.
Excellent.
There's a lot of questions.
Let's go for it. I'll wait for the third one on the screen there. But let's go with the ever-improving understanding of assemblies, AVB, insulation, rain screen, glazing, etc. Where do you see the next leap for performance and carbon in facades?
I think that's probably a question for me. I think the next big kind of new and exciting technology is vacuum insulated glazing and thin triples. I know I had some conversations with the NBBJ folks, and I know the micro pillars and the VIGs are not, aesthetically speaking, they're not ideal, but when you stand far enough away, you can't really tell. And for those of you who aren't familiar with VIGs or thin triples, they're basically glazed products, so vision glazing products that can achieve R values of up to R10 to R14, which is pretty amazing because those are types of values that you would want in an opaque wall, not even just curtain wall spandrel, an opaque wall. And the other great thing about those is that, with vacuum insulated glazing, it's thin enough that you can actually replace single glazing without having to change out the framing. With thin triples, it's sort of the equivalent, but having a triple glazing in a double glazed unit frame. And aerogels, but they're too expensive.
For vacuum insulated glazing, do we have those manufacturers in the room? If you could raise your hand, we'll come tackle you during the happy hour. If would love to know more.
Vitro is here, right?
Well, I think he's coming back for the happy hour, so yes, he will be here.
Perfect. Look for them.
Yeah.
That's fascinating technology. I am going to go to the last question because I want to give all of you a chance to answer this, and that would be, what's next? Thinking of the future, and I'm adding my own twist on this, sorry for whoever's question it was, thinking of climate change, materials, AI. If you can phrase it within, I was going to say one word, but I'll give you 1 or 2 sentences. What's next?
So I think what's next and what's needed is consensus on methods for calculating embodied and operational. Right now, there are a lot of different tools that use different methods. So I think more transparency on approaches to calculations and kind of coming up with a unified method is needed.
My secret desire is that all of these special things that we do and differentiate on become totally commoditized. Like the future I want in 2028, 29 is where doing LCA and all these carbon analyses are the floor, and not an ad service, right? That's where I want the industry to head in the next few years.
I want the industry to normalize the use of morphed weather data so that we're designing, I mean, Jack mentioned, better predictions, right? We can't really have better predictions of our building's energy use if we're using historical data when the climate is changing as fast as it is. We have to be using future predicted weather data, and that's based on statistical modeling. It's meteorologically correct, and you can choose your emissions scenario. So there's a range of options that you can decide on.
Excellent. Thank you all. Hopefully we're all feeling energized.